Welcome to the last lecture of the semester, actually, finally. We will talk today about reinforcement learning. We talked a lot about supervised learning, we talked a little bit about unsupervised learning. We actually hear today about the third paradigm in machine learning, that is the most general one of it. And we will do it not as a complete introduction into this branch of machine learning. We take a different approach. We look into one specific example that has become quite famous in the last years, the AlphaGo example. And what we will try in this lecture is having a complete understanding of how it works. Then we know one approach to reinforcement learning in detail, and we know what in general is different in reinforcement learning from supervised learning and unsupervised learning. And from there you can start exploring for yourself which kind of application is most interesting to you. We will first hear what is reinforcement learning. We look in detail into the example, and then we will look into how this example is built. How does the training work? This is just how is it applied. That's the idea. In the end, there is an exam, no, not an exam, an exercise, where you can try out the stuff for yourself, not on Go, but on tic-tac-toe. Also ends on O, also a game, a little bit more simple, and you can program it probably within 4 hours or so. There's a code skeleton, and you can work on that if you're interested. So that would be the plan for today. Let's get an idea of what AlphaGo is about in the words of one of its inventors, Professor David Silver, in his own words.
AlphaGo Zero is the strongest Go program in the world. It outperformed all previous versions of AlphaGo. Specifically, it defeated the version of AlphaGo that won against the world champion Lisa Doll, and it beat that version of AlphaGo by 100 games to 0. So all previous versions of AlphaGo started by training from human data, and they were told, well, in this position, the human expert played this particular move, and in this other position, the human expert played here. AlphaGo Zero doesn't use any human data whatsoever. Instead, what it has to do is learn for itself completely from self-play. So the reason that playing against itself enables it to do so much better than using strong human data is that, first of all, AlphaGo always has an opponent at just the right level. So it starts off extremely naive, it starts off with completely random play, and yet at every step of the learning process, it has an opponent, a sparring partner if you like, that's exactly calibrated to its current level of performance. And to begin with, these players are very, very weak, but over time they become progressively stronger and stronger and stronger. People tend to assume that machine learning is all about big data and massive amounts of computation. But actually what we saw in AlphaGo Zero was that algorithms matter much more than either compute or data availability. In fact, in AlphaGo Zero, we used more than an order of magnitude less computation than we used in previous versions of AlphaGo, and yet it was able to perform at a much higher level due to using much more principled algorithms than we had before. I think I can speak for the team by saying that we were all pleasantly surprised by just how far it went, that eventually it was able to surpass all of our expectations, and it was able to actually climb up the ratings until after around 40 days we found that it had actually defeated all previous versions of AlphaGo to become the strongest Go program in the world. And this is all for a system that's been trained completely from scratch, starting from random behavior and progressing from first principles to really discover tabula rasa, how to play a game of Go.
I think this is a very interesting statement that he made here, and for me the take-home message of all the work in AlphaGo Zero, that he said, usually people think in machine learning what matters most is the availability of massive amount of data and massive amounts of computation. And he said, we found out in this project that that's not true. What matters most is the availability of very good algorithms. It matters much more than the data or the compute. Yes?
I think I missed something. What is Go?
Go is a board game like chess. A Chinese strategy board game. You can maybe compare it to chess. I will later explain about the rules a little bit, so we have a common understanding. So it's a board game. It was, I will talk about it later. But the take-home message here is, it's actually not that you can take any algorithm as long as you have lots of data and lots of compute. Machine learning is about clever algorithms. And sometimes this has to be reinforced towards stakeholders that say, we don't have data, or, it's easy what you do. It's not easy. Building a successful machine learning system is hard work, and it's about the algorithms. And then, of course, you need compute and data. What we will do now is we will take this system apart until we understand the basic idea, up to the point where you could program it. So, and that's possible because it's a really elegant system. And by that, you will learn something about reinforcement learning. But be warned, reinforcement learning is a much more diverse field as machine learning per se. I have the impression, at least for myself, that for machine learning I somehow have a map in mind, how everything fits together. Even if there are thousands of algorithms, there are guiding principles, like the inductive bias, you know how to do experiments, how to evaluate it, and then algorithms differ, but there are principles that fit together. You can explain algorithms by their representation, their optimization, the features they use. So somehow in my mind this forms a map of machine learning. In reinforcement learning it's much more diverse. Different approaches solve a similar problem, but with a complete different approach. So we will look into one specific example today, and I hope you can extrapolate a little bit on what is behind the technology. So you would be able to start working on it. You will not be an expert in reinforcement learning afterwards, but you know one very good example in detail. So first, let's see what reinforcement learning is. Usually, and I took that from the lecture slides of David Silver himself, usually you have a diagram like that to explain what is a setting in which you would use reinforcement learning. You usually have an environment. Could be a game, could be the real world, could be whatever thing it is your agent, your software, your program works in. That's your agent. Maybe it's not a good metaphor to have a brain here because it lets you think of AI as something that is modeled after the human brain. It's not, you know that. The agent, the thing we want to build, model, and the world, the environment. And reinforcement learning is the kind of machine learning where your agent interacts with the environment. It issues actions, something that it does, and it receives observations. Imagine a robot with a camera. With a camera, it senses the environment, it receives observations, and then it does actions, like it's going forward, backward, sideward, grabbing something. And it's just learning in that process of acting in an environment by sometimes receiving a reward. And it's not like in supervised learning, for every action you do, for example classification, you directly get the result of true or false, or correct or incorrect. The reward can come very much at the end. Imagine you want to build a robot that plays robot soccer. A reward in soccer you only get when you win, or you could say when you score a goal. But soccer is a low-scoring game. There's only a goal every so and so many minutes or hours. So the reward can be very sparse, and you get a lot more observations and do a lot more action than you receive reward for. So a problem in reinforcement learning is, given sparse rewards that comes delayed, like you can do lots of good actions that lead to a goal eventually later. Your problem is, how can you learn from this kind of very sparse feedback? So in reinforcement learning, it's all about interaction with an environment rather than having a set out data set on which you can learn what's in that data set. You're interacting with an environment and you're learning directly from that. This is the most general of all machine learning settings. Biological learners, humans, cats, whatever, most of the time when they learn in such a setting. You're placed in some setting, in an environment, and you start acting and trying out what does different actions do. Learning on the job, so to say. Reinforcement learning is this. And this already shows you why this is also a complicated thing, a thing that you cannot expect to work out of the box as well as supervised learning. You get much sparser rewards, and it's much less defined what you actually want to learn. In supervised learning, in classification, you have a loss you want to minimize. And for every attempt you make, you directly get reward. Yes, no, correct, incorrect, you get a loss, you can adapt your weights, whatever. In reinforcement learning, you want to maximize cumulative reward. So for a lifetime in the future, you want to collect as much reward as possible. But in the beginning, you do not know what actually brings you reward. In the game of chess, you usually play, I think, around 40 moves on average until you either win or lose. From this, you have to deduce which one of the 40 moves was a good one, which one was a bad one. You have to play a lot of games until you find out this. So in reinforcement learning, you usually have the problem of having a trade-off between exploring new actions and seeing the feedback of the environment. What observations do I get then? Do I get a reward then, a positive or a negative one? And exploitation, doing what you have already learned. When you have learned for some time, for example, I as a teacher now have 6 years experience of teaching at ZHAW. When I'm always doing what I learned works well, then I will never improve again. If I try to learn from the evaluation you just gave me, I can still improve, but that means exploring new stuff that could also go very wrong. If I only exploit what I already know, I will never improve again, but it will also never, something unexpected will happen. But in order to improve, I have to explore new things, and that could go horribly wrong. This is a trade-off that reinforcement learning agent is in. He can just learn by interaction. He has to explore new things and at the same time exploit what he has already learned in order to rise in performance, not just act randomly. So just by these characteristics, you can see it differs a lot from supervised learning and unsupervised learning in the way the feedback and the learning process is designed. It's not anymore about data sets. It's not anymore about for every input you know the output. It's interaction with an environment. For every time step, issuing an action, receiving an observation, and sometimes receiving a reward. Or always receiving a reward, but sometimes it's non-zero. So that's the general setup of reinforcement learning. All these different algorithms, versions that have not much in common, all have the same in common, that they solve such a problem, such an environment. If you want to come back to a principle we learned about in the very first lecture, bless you. We learned there about the principle of the inductive bias. Right? Every learning algorithm has something built in that makes it look for specific patterns in the data. And if what is built in the algorithm actually fits the patterns you're looking for, then this will usually work out very well. And we have talked about learning algorithms with high inductive bias that are looking for very specific things, linear regression, for example. If your problem is really a linear problem, it will work like a charm. If your problem is all but linear, it will not work at all. If you take a low bias algorithm like a neural network, it can almost learn anything, but it will learn very slowly with lots of data because it has to learn all these biases from the data itself. Given that, this tells you why there are so many completely different reinforcement learning algorithms. If the setting itself is absolutely general, just learning by interaction, and it takes much more care to select an approach that suits the exact problem that you want to solve, so it has a chance to learn anything, because the setup here is so very general. I think this is the reason why there are so many reinforcement learning approaches. And why, when you know one, you cannot just take this and apply it everywhere else, and it will work. Usually, the approach and its success is very much, it's intimately linked to the specific features of the problem you're trying to solve. So an algorithm that works well on Go is not, or chess is not supposed to work well on robot control. It could, but it's not necessary. Okay, that's on general reinforcement learning. What open questions exist? Yes?
Is it correct to say that we always need to be able to simulate the situations in which we want to learn? If we cannot simulate, we cannot learn it.
The question is, do we need to be able to simulate? Like, do we need to be able to simulate the environment in order to have a closed loop of simulation and our software that is somehow controlling something? You can also say reinforcement learning is learning to control something, steuern. Of course, it is helpful if you have a model here with which you can produce as much observations as possible. That's called model-based reinforcement learning. But it doesn't need to be like that. You can also plug the agent directly into a real environment. Of course, if you have a simulation model at hand, that helps a lot, because you can basically speed it up a lot. But it's not necessary. You can also learn, for example, with real hardware in the real world. It's just running in real time then, not much faster. But example, Google, for example, has a lab where they have a big hall full of robot arms that are trying different tasks, like grabbing balls and putting them in different boxes, all in the real world, because they found out they can only model so and so much in a simulation. At some point, it becomes tedious to model all the physics and make it very, very accurate, so that you need, in the end, if you want to make it useful in practice, you also need to do it in the real world. And so they have this huge lab, this huge building, where there are just robot arms doing the stuff in real time in the real world, training. So you do not need a model, but if you can simulate, this is of course very helpful. And at the moment, many of the breakthrough kind of things concentrate on games and things where you have a physical model and can simulate stuff. More questions? Yes?
You say when you play software, you get very huge rewards. But can't you say if you control the ball for a longer time, or if the ball spends more time in your opponent's part of the field, it's already a better state?
Yes. The question is, at the example of soccer, yes, rewards in terms of goals is very sparse, but can you not come up with different reward functions where, for example, controlling the ball for a long time is rewarded? That would basically be a RoboCup team that is modeled after Pep Guardiola's style of playing soccer, just holding the ball. Yes, you can do that, and it's done a lot. It's called reward engineering. It's exactly the same what you do in other machine learning parts with feature engineering. You put a lot of effort into finding the right features, or here the right reward function, so that learning becomes more easy. The problem is, of course, when you start optimizing manually the reward function and putting lots of energy into it, yes, learning becomes simpler then, but also the method loses a lot of its generality. So usually it's a trade-off between how much effort you want to put into shaping the reward function. It's actually called reward shaping, sorry, not reward engineering. You only want to put so and so much effort into reward shaping, otherwise this thing will not generalize. But in many applications, this is part of what is being done to make it run. Making the rewards a little bit less sparse and a little bit more well-behaved.
Is there a possibility to take multiple rewards? Because to say, if it gives a goal, it's more weighted than, for example, to take the ball longer or to have the ball for a longer time, but it's also a reward, so that you can, yes.
Question is it possible to have multiple rewards? Yes, exactly in the same way as you can have multiple components in your loss function. You can have multiple components in your in your reward function as well. Again, there's a trade-off. You do not want to put all the intelligence into designing a reward function that makes learning then very, very easy, because then all the learning is again done by humans. But that's possible, and it's also part of what is being done. Okay? Application areas. Until, I would say for myself as somebody who not so long ago started delving into the topic. For me, maybe 1 or 2 years ago, reinforcement learning was a very, very interesting intellectual exercise with not too many application areas. I was very delighted to see last fall that a reinforcement learning meetup group started to assemble in Zurich, and it was completely industry-driven. It's hosted by a guy from Swiss Re and Nico. They usually sponsor an apéro and a room full of experts, like as much people as are in this room today, assemble for evening lectures to listen to people who use reinforcement learning somewhere in business. So the stuff is really useful. It starts getting useful at the moment, and it's a very, very interesting area to be in. It is connected with lots of hardships, lots of disappointments, many things you try don't work, if you make it work. So, what can you do? Of course, you can do automated vehicle control. These kind of things where an automated helicopter is doing very complicated flight moves was one of the very first interesting use cases done by Andrew in Stanford. Chatbots, learning to control what is the right reaction can be done. The outer loop, so to say, over the chatbot could be done by reinforcement learning. It is done in some applications. Creating a medical treatment plan, like, okay, first we do this, and then we do that, and then we do this, and then we have a branch, and we can either go here or there. Everything where you need to do a plan, where you need to come up with something you can control, can be done by reinforcement learning. So medical treatment planning can be done by it. Not just classifying if a picture shows cancer or not, but then planning, okay, what to do next. Do I need to take another image to be more sure? Do I need to, probably not fully automatically, but this can be a proposal towards a doctor. Gameplay, this is what we're talking about today. Lots of the great examples of the recent years have been in gameplay. Not just games like chess or Go, but also capture the flag with a Quake 3 engine and things like that. Data center cooling. This is actually what Google did with the research that was done in the AlphaGo case. Rumor has it that Google paid originally $500 million for the company DeepMind that just did some reinforcement learning on games. And with this one application of having a more efficient data center cooling strategy orchestrated by a reinforcement learning model, they saved money in much higher numbers than they originally paid for the company. So there's lots to gain out of it. Database query optimization, like how can you deduce a query plan for having quicker access to large databases, has been started to be done with reinforcement learning. And a very interesting thing actually, learning new machine learning algorithms. We talked very quickly at the beginning of the ensemble lecture on learning to learn in two different ways. Meta-learning in terms of ensembles and meta-learning in this respect. If you're interested, read this blog post. Good, so these are some things where the stuff can be used. Let's look into one example, and this is an example of Go, a board game. The former world champion, Lee Sedol, versus AlphaGo, the software trained by Google DeepMind. And as you might have heard, in 2016, he, very much to the surprise of everybody, lost the fight against the machine. Why was it a surprise? I mean, 20 years before, Garry Kasparov lost against a chess computer, and that was also to the surprise. Chess and Go have some things in common. It's a board game with figures. Why was it such a big surprise? Some figures about the game of Go. The problem in Go is that it has a very big search space. Like, from one action you take, all the next possible action. There are so many possible actions you can do in every move that there are, from now to the end of the game, a huge number of different states you would have to search in order to be sure which one is the best move. In chess, this was a problem 20 years ago. Go is an order of magnitude higher in the number of possible game states. And if you want to play a deterministic game where there's no chance involved, there's no invisible things where you have to guess, it's completely deterministic. You can do perfect play if you just search all possible states and go to the ones that lead to your desired result. But it's impossible, even with modern machines, to solve that exhaustively. So the problem is, how can you search, not completely, but only those areas of the search space that are somehow rewarding. And this is something a human can learn with intuition, and that wasn't possible before with the computer approach. So, how does it work? Go is played on a 19 by 19 board. Is any Go player here? If I tell you complete bullshit, please correct me. I've just read about it. But it should be more or less correct. A good thing is, it's two stones, blacks and whites. You play alternating, two players play alternating. There are only two possible outcomes. There's no draw, it's either win or lose. That makes it quite easy for machine learning things. There's no third state, it's binary in the end. And the rules are as such. Each turn, it's one player's turn, he takes a stone and puts it at some junction on the board. You see here, there's a grid, and you can put a stone on any free junction. You can choose which one. Or you can pass, you can do nothing, and give the turn to your opponent again. If you surround stones of your opponent completely and directly with your stones, you capture the stones of your opponent and they are taken from the board. It's not allowed to recreate any board position that has been on the board previously. So you're not allowed to go back to any configuration of the board that you already were in. That means you're not allowed to somehow go into a safe position where your enemy can do nothing. That leads to you either win or lose. There's no ties. If you cannot move for 2 consecutive rounds, you have lost. And cannot move means you cannot move without recreating something. And if the game is, no, you do not lose, the game is over. And if the game is over, the area that the black and the white stones cover are counted, and the one with the larger area wins. So basically, after the game is over, reward +1 is given for the one who wins, and -1 is given for the one who loses. That's a game of Go. It's the most complex strategy game that is well known. It is played in China since a couple of thousand of years. It's much more complex in strategies you can use than chess. And that made it, until AlphaGo 0, AlphaGo arrived, made it impossible to play by computers. Well,
how do you remember all the states the board was in, so you don't accidentally go back to a state that was already?
I actually don't know. The question was, how do you remember all the states you were in?
It's only you can't go back to the state you had before.
Is it like that? I read in the rules yesterday, and there it was, you cannot go back to any configuration.
I just remembered this way from, we had a presentation in deep learning about it, and there they said you aren't allowed to go back to the last step you were in.
It's possible that it's like that. In the previous version of the talk I gave, I also said this, because there was a Go player in the room that said it's like that, you're not allowed to go back to the immediate last position. But I had to look into the rules yesterday because I was unsure, and there it says you are not allowed to recreate any board position. But there are roughly 100 moves on average per game, so you wouldn't need to remember 99 of them. I'm actually not sure. Probably it's like the colleague said, and it's just the last one, but I'm unsure. So the rules give you a lot of freedom what to do, and there are actually huge books for specific opening strategies and so forth. There's a very big richness of what you can do with these rules in order to play it. This is the cover page of a series of successive articles that became famous, all on this system produced by Google DeepMind. The first one is on AlphaGo. It made it to the cover of Nature. It was a great thing. Then there was AlphaGo 0, the one we will be talking about today, which improved on this in terms of performance a lot, and actually made the system much more clean and simple. And then there's Alpha 0 without the Go in it. It's still the same than here, but they made it more general, so they can apply this very same algorithm also to chess and to shogi. Shogi, you probably never heard. It's a Japanese version of chess, so to say. Also a board game, also 2-player, also strategy. So they showed it can not only play Go, it can also learn the rules of chess and another similar game. The interesting thing here is, and that is very seldom in machine learning, this is why I present it to you. This was the first breakthrough article. The system is quite complex, difficult engineered, lots of training, lots of data. This is what David Silver talked in the video about, that it is. It needed supervised learning and expert knowledge from human players, and for every board position, what would the human do to start the learning process. This system became much better, with much less data and absolutely no supervision. It just plays against itself. And then this is just an extension to show how general it actually is. It means playing strength went up, generality went up, complexity of the method went down. What that usually says first, this is completely rare. Usually in science it's the other way around. And it shows that they have discovered something beautiful here. Something that is really, it deserves a look, because they discovered something that has some generality in it. And this is why I want to explain. Good. Let's see how we can apply the AlphaGo Zero system. After that we will make a break, and then we will see how we train it. So, what is the goal of learning? The goal is a policy. You remember that picture of how reinforcement learning in general works. We have here the environment. The environment would be the Go board and the opponent. The observation we make is we see the current state of the board. Like what happened after the opponent moved his stone. Our agent gets this observation and should output an action, like our move. This somehow changes the environment, it changes the board, and we will see the next observation, like what did our opponent do after us. And sometimes, namely when the game is finished, we will receive a reward, +1, -1. Our agent could actually be modeled or written down as a specific function. A function that gives you, for any given observation, input, the probability per possible action. So the probability of any possible action given the current state. And this function that is giving that quantity, the probability of each possible action given the state, is called the policy. And it's usually called pi. Pi for policy. So pi, or policy, is a function that we want to learn that takes as input the state and outputs a probability distribution about all possible actions. All possible actions would be every junction on the grid, on the board, and the probability that we should place a stone there. Of course, that makes a connection to machine learning obvious for you that knows supervised learning. We could do that with a function approximator. We could plug in, for example, a neural network here that takes some representation of the board state and outputs a softmax vector, thank you, with the probabilities for every possible action. So we could represent our brain here, that was here as a placeholder, by some sort of neural network that takes in somehow the board. You can imagine it as an image or whatever, an array, and it outputs a softmax layer. Every neuron represents one specific action, and the number here will be the probability of that action to be taken in that state. So you could model it like that. When you have the optimal policy, like the policy that always maps the current state to the best action so that you win in the end, then you can use it in the following way. You start playing, you receive the first state, you look what is the best action, you take that action, you get the next state, and you do this until the game is over, you will probably have won with the best policy. Problem is the following. In a complex strategy game, it's very hard to directly go from input to best possible action. Like directly, like out of gut feeling, out of intuition. It is not what a human would do. Have you ever played chess? Have you tried to think in advance a couple of moves to see, okay, when I do this, then my opponent probably does this, and then I will react like this? And usually for me, then it's over. But a very good player can do this for, I don't know, 7 moves ahead. you not just rely on your intuition, which of the current moves is the best one, but you try to think ahead a couple of moves, always using this intuition, because 7 moves ahead, you are much closer to the end. You will have a better estimate of the end. So you do this planning ahead. This we could call a strategic look ahead to let tactical behavior emerge. The function approximator is something like intuition, a gut feeling. Oh, I see the board, I should do this. A look ahead search would add some tactics, some more thorough planning to the intuition. How could that look like? Imagine you have a board, and now you plan. Okay, what happens if I play like this? Then we arrive here. Maybe not so good. What happens if I move here? Then I will arrive here. What happens now? You simulate in your agent a couple of moves ahead. How could you do this? Each time you could use your network or whatever function approximator you use to do an intuitive decision what is best in that situation. But you do not just stop there. You do not just take this action for granted. You simulate further. Okay, what happens now? What would my opponent do? What would I do then? How would he react? And so forth. Until you see a couple of moves ahead, which one really plays out well. And these two things combined, the intuition from the function approximation and the look-ahead search through a just search algorithm, really can produce a good result. And these two ingredients will be the main ingredients in AlphaGo data. So, imagine we have a learned policy. That means we have a trained neural network, or whatever kind of machine learning approach, but here it will be a neural network, that takes the representation of a state, outputs probability per action. How would we play with this? We have the neural network. We usually call it f, it's a function, parameterized by the weights of the network, summarized by theta, as we did in the very first lecture with all the parameters of the method. It takes as input the state, and it outputs two things. This p vector is a distribution about all possible actions, probability per action in that state, like which one should they choose. And v is called the value of the state. That is the probability of winning when I am in that state. That tells you somehow how desirable is it to be in that state. If you imagine this tree search kind of thing, when you're here and you want to know, is it a good state, should I plan ahead from here or should I go to another branch, it's important to know how valuable is that state compared to this state. For this, you do not need the distribution about the actions, but you need an estimate of the value. How probable is it for me to win here? So imagine we have that. We have a neural network, it gives you for every possible state an estimate of the probabilities, the actions, estimate of the value, probability of winning. That gives you the intuition. And then we have a second important method, it's called Monte Carlo tree search. That gives you the tactical behavior. What is Monte Carlo tree search? It's actually a standard tree search. What does tree search mean? It's a fancy name for a simple thing. Anyway, we'll not be on the video. Imagine this game. It's much simpler to draw. Tic-tac-toe. When I put my cross here, what are the possible next moves of my opponent? The opponent could put the O in any of the 3 cells, right? So we have 1, 2, 3, 4, 5, 6, 7, 8 possible successors in the next level of the tree, right? And the first one would probably look like this. Okay? And the next one would probably be this. And from here, what are the possible actions? I could put my x here, 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 or here. 1, 2, 3, 4, 5, 6, 7. And the first one could look like this. And from here we have 1, 2, 3, 4, 5, 6 possibilities. This is a game tree. It just shows every possible configuration of the board successively, starting from where we currently are. And a tree search implicitly builds up this tree and looks for which positions are desirable in the very lowest level if the game is over. And then it looks, okay, how did we end up there? This is what a tree search is doing. Of course, when I told you the game of Go has 10 to the power of 170 different states, it's impossible to build this complete tree. You cannot even hold it in memory, lest compute everything. So we need some randomization. We cannot look at every possible state. And this is where the Monte Carlo comes in. Monte Carlo actually refers to the casino in Monte Carlo and the randomness that is involved. And Monte Carlo tree search does not look at every possible state in the game state space in the tree, but only at the most likely ones. We will see in a minute how that works. So let's say we have these two ingredients, MCTS and the neural network. We have it trained somehow magically. How do we choose each move? We are in a specific state currently. We put that into a Monte Carlo tree search. Monte Carlo tree search takes the current state, generates all successor moves because it knows the rules of the game, so it can basically say what is possible. For every successor state, it invokes the neural network to see, okay, what action has the highest exactly, thank you. The highest probability. It looks from there and we play the game to the end. And we do this a couple of 100 times. And then some of the paths will be beaten more often because they are more probable. And these are the ones we will focus our research. We will make that more clear in the next couple of slides. How do we perform the Monte Carlo tree search in detail? We are in the current state, it's our turn, we want to perform the next move. What do we do? We create an empty tree, where we just have the root, our current state. And then we have a loop for, in the paper, is 1,600 times. This is a hyperparameter, it could be 1,000 times, could be 3,000 times. It just worked for that. What do we do in each of these loops? We start at our current state, here. And then we go down the tree we currently have. In the very, very first iteration, of course, there are no more nodes. We just have the root. But let's imagine we are not in the very first iteration, but already in the so-and-so manys. So there's already some tree. And now we traverse the tree, meaning we are in the current state, and each vertex here leads to a possible next game state. And each edge has attached to it 4 different numbers. What are these numbers? N, the number of times this action has been taken already in the run of the simulations. So we just count how often did we come down that path. W, the total value of the following state. That is just the sum of the values that come out of my neural network. This B. Q, the mean value of the next state. This is just W divided by N. And P, the prior probability of selecting action A. This is the probability that was originally outputted by the neural network. We will just see in a second how we originally arrive at these numbers. They are at every edge in our tree. So we traverse the tree. How? We are here, we want to know where do we go down, here, here, or here. How do we do this? We calculate for every action, for every branch, what is the value of Q plus U? And we choose the branch which maximizes Q plus U. What is Q? Q is exactly the number that we store here, the mean value of the next state. You remember? The value is something the neural network originally gives us. So this originally comes from the neural network. When we come down a certain path 1,000 times, we will have evaluated that value quite often. So this value will be quite stable in a statistical sense. It will be the mean over many iterations. So we can have some trust in it. But in the very beginning, when we just do the first iteration, this Q value is not something very reliable yet. It's a mean value over 1 or 2 simulations. So we cannot rely much on the mean. So then we rely more on U. And what U is, it doesn't matter too much how you compute it really. It's called an upper confidence bound. But it has to do with the prior probability of this action as originally given by the neural network. So if the neural network, the intuition module, originally says this action has a probability of 80%, then this will be somehow related to the U value, and we rely on this. After a while, when coming down here more often, the mean value Q becomes more reliable. We will ignore the U, just focus on Q. So we will, in our simulation, traverse a tree by always choosing the branch where Q plus U is maximized. We go down the most probable path we have so far seen. Next thing, we arrive somewhere where there is no further node, because we built the tree on the fly. What do we do when we arrive here and there is no further node? We invoke our neural network. And this is how all the other nodes came into existence as well. What do we do with the neural network? The neural network takes in the current state, this thing. And it outputs the probability of all actions, the prior probability of all actions, and the probability of winning from the next state. So we will take these numbers, and with these, for every possible action, we will create these nodes and create these initial statistics. That n, the number of times you came down here, is of course 0, because we have never seen it before, we just created. The w, the cumulative value of the next state, is also 0, because we never came down there yet. The q value is also 0 yet, because we have never seen it yet. The only thing we have is a p value. P, the prior probability of selecting that action, this branch. This is just what comes out of the neural network. So the correct cell in this vector that corresponds to the specific action. So when we come up to the end of the tree, we invoke the neural network, we create a new branch, and initialize it with the numbers we get from the neural network. We initialize it with the gut feeling that the neural network provides, given that this is trained somehow. And then the next step is important. As soon as we created that node, we back up the statistics of all the nodes and edges in our path. We increase for every edge in our path from the root to where we currently are in our simulation, the number of times we visited that node. We just increase it. We increase the sum of all the values by adding the v from this node that comes out of the neural network. And we increase the mean value, or recompute it, by just computing sum of all the values divided by number of times you visited it. And the p stays constant. It always remains what we got from the neural network. By this repeated process, 1,600 times, we build up a tree that overall we run 1,600 times until the end then of the tree. We probably come down not to the very end of the game, but quite far. And we will more often go into those paths that are more probable. More probable with respect to what initially the neural network said, and more probable with what after some time the simulation says holds true. This is how the Monte Carlo tree search works, by ad hoc building the tree and focusing on those paths that are most probable, and not creating everything, because that's impossible. Questions?
Can you have a break?
Yes, I think that's exactly the plan now, to have a break. Shall we? Are there any questions we should discuss before the break?
How long is the break?
Let's make a break. We make break until 2:50.